Swayam Prabha. Digital India. Educated India.
Kothari, Assistant Professor in the Department of Computer Science and Engineering at IIT Madras. His research focuses on graph theory, matching theory, and important areas of theoretical computer science. He completed his PhD at University of Waterloo, Canada, and has held research positions in Brazil, Austria, and Canada. We are honored to have him with us today. Please join me in warmly welcoming Professor Nisha Kothari.
Thank you very much. Hi, good morning. Am I audible? Yeah? So thank you very much for the nice introduction. It's my first time teaching in this setup, I guess. Is this something that happens every year or is it something new? Happens every year? Okay. And you all are from schools around Chennai or in Chennai? Okay. Okay. What grades are you all in? 11th and 12th. Okay, cool. Right. So, I'm going to talk about an area of mathematics and theoretical computer science. In the general, generally people think of computer science and mathematics as very separate, but in reality, computer science actually has its foundations in mathematics. So, although I'm in a computer science department, basically what I do is mathematics, and I want to show you a flavor of mathematics that maybe the high school curriculum doesn't expose you to. So that's what I'm going to do. How many of you have heard of this thing called the 7 bridges of Koinsberg? Okay, cool. Good number of you have heard of it. I'll write it down in case it's not very audible, right? So, the 7 bridges of Koinsberg. So, Koinsberg was a town in Prussia. My geography is not great because that's not what I specialize in. But today it's in Russia. So, Koinsberg was in Prussia. This was a country or a state back in the day, and now it is basically a town in Russia. Right? So, in 1736, right? So, we are going back quite a few years. How many years is it? Almost 300? Is it 300 years? 290, thanks. My math is not great. Cool. So, right. So, the king of Prussia had this problem. So, people would come. So, this was a touristy city. So, a lot of people would visit the city or the town, and there were these 7 bridges. So, the bridges here, my drawing is not great, as you can tell. There are 7 bridges, 1, 2, 3, 4, 5, 6 and 7. And what you see in blue is rivers, right? So, there are some water bodies, and these bridges are built over those water bodies. And these are the land masses. So, this is sort of a snapshot of 1736 Koinsberg. Of course, all the beautiful details have been omitted. Only the water bodies and the bridges and the land masses have been shown here, right? So, this is what the city looked like. And what the tourists would like to do is they would like to check out every bridge. Apparently, these bridges were very beautiful or something, I don't know. I did not live in that time. So, they wanted to check all the bridges. But of course, they did not want to repeat a bridge, right? It's too much effort. Human beings are lazy, so we don't want to repeat the same bridge again, right? But we want to see all the bridges. We don't want to miss out because we have very high levels of FOMO, right? So that was the problem. So the king of Prussia was wondering whether it was possible to actually visit all the bridges without repeating any bridge. Is the problem clear? So I want to start at some point in the city. I want to go to this bridge, then I'll be in this part of the city. Then I will go to this bridge, then I'll be here. Then I will take one of the other 4 bridges. I want to do that. but I want to never repeat a bridge. Is the problem clear? Yeah? Okay. So, well, I mean, the king did not know whether this is possible or not. So, they employed a famous mathematician called Leonhard Euler. So, they brought in Euler and they asked Euler, hey, is this possible? Can you actually go through all the bridges without repeating any bridge, right? So, well, I mean, Euler also did not know. Euler had to spend some time on it, I guess. So, what Euler did is, Euler realized that there is too much information in this picture, right? Although I have removed all the unnecessary details, there are no buildings and there are no beautiful museums or whatever. But even then Euler was like, there is too much information here. Let's simplify this further. Yeah, does it make sense? So Euler introduced a new mathematical object which is today called graphs. That is my area of research, graph theory. But this was not there in 1730s. Nobody had studied graphs formally. We didn't even know what they were. So Euler was like, I'm going to define a mathematical object using this picture. Yeah. So Euler said that, look, I don't need so much information. I need to know what are the land masses. How many land masses do you see here? Land masses? 4. Yeah, you all agree? There is 4 land masses. Yeah. And how many bridges do you see? 7. So what Euler said, I just want to put a point. We will actually change this word later. Right now I am going to call it a point. So for each land mass, put a point. Okay. So let me call these land masses L1, L2, L3 and L4. Yeah. So my points are going to be L1, L2, L3 and L4. 2 land masses. L1 and L2, or let me just say for each bridge B joining 2 masses L and L prime or L dash, what I will do is I will put a line joining those 2 land masses. Put a line joining them in this picture. Okay. So let's do that. So I've drawn the bridges in pink. So maybe I'll stick to pink. Let's call them P1 to P7 because I lack creativity. So P1, P2, P3, P4, P5, P6. Why did I call them P? B. So can someone tell me what should I do for B1? What are the land masses that B1 joins? L1 and L2. Yeah? Okay. So L1 and L2 joined by B1. Is there any other bridge that joins L1 and L2? Any other bridge that joins L1 and L2? B2. Okay. I'll draw another line joining them. Yeah. What about other bridges? So let's say what about B3? What does it join? L1 and L3. L1 and L3. Yeah. What about B4? L2 and L4, right? Is it? Yeah. Okay. B4 is L2 and L4. This is B4. Are there any other bridges joining the same 2? B5 also joining the same 2. Okay. B5 also goes like this. Yeah. And what about B6? L2, L3. L2, L3. And finally, we are left with B7, L3, L4. L3, L4. Yeah. Looks ugly, but it is what it is. Yeah. Everybody okay with this? Yeah. So, this is what Euler called, I don't know if Euler actually called it, but today we call it a graph. Okay. So, I'll talk more about what a graph is, but is this particular example clear? Right. So, Euler said this has enough information to figure out whether this is possible or not. What was the question? The original question was, in the city of Koinsberg, is there a way to visit all 7 bridges without repetition? Yeah, this was the original question that was posed to Euler by the back then king of Prussia, right? And Euler constructed this. This is not an answer to the question. The king was like, you are good, you are up to no good, do something useful. So Euler was like, I can actually ask the same question in the language of this graph, or in the language of what is today called graph theory, right? So that was what Euler did. So can we all try spend some time to think about what does it mean in that city being able to go through all the bridges without repeating? What does it translate to in this graph model that we have constructed? And if you have an answer, don't shout it out. Just discuss amongst yourselves and raise your hand and I'll come and talk to you. Yeah? But yeah, just discuss with your neighbor and then raise your hand and I'll come and discuss with you. Yeah? Let everybody have the opportunity to explore and think.
So it's related to the number of lines coming out of each node, if it's even or not.
I don't want the answer. I don't want the answer. If you've already seen it, that's not enough. I'm looking for the way of thinking. Yes, I'm not looking for, if some of you have already seen this, I'm not looking for the answer. The answer doesn't have any joy for me, right? What I'm looking for is just the way of thinking. So can you just think about translating between these two and see if you can come up with a way to explain what does it really mean in this graph, this specific question, right? If you already know the answer, that's okay. Try to still think freshly. Yeah. Yeah, raise your hand, raise your hand. Raise your hand, I said. Don't ruin everybody's chance to think. Yeah? Yeah.
Go through all the points and land at same.
Slowly.
Like if we start at L1 to land at L1, go through all the points B1, B2 and land at L1 again.
Land at
L1. If we start at L1.
Why is it necessary? Was that the original question? See, the original question doesn't say you have to come back to the same point. The original question just says you have to go through all the bridges without repeating. So even if you start at landmass L1, if you end at L4, it's okay. So think again. Yeah. So Yeah, so what I'm looking for is just a translation of the problem. Yeah. Just think about that original question. What does it really mean? That's all I'm looking for.
If that's wrong, then each node should have only 2 pages.
So again, I'm not looking for an answer. I'm just looking for a translation of the problem. Right. So just to clarify, I'm not looking for an answer to the problem. Right. I mean, this is not a contest where like, oh, who got there fast? That's not what I'm interested in. Right. Competition is the last thing that excites me in life. I'm just looking for a translation of the problem statement. Right. So the original problem is stated in terms of a city. Right, which is something we all understand. We all know what it means. In Chennai, if you make a map of Chennai with all the bridges, we all know what this question means. Going through all the bridges of Chennai without repeating a single bridge. So that's the original question, stated in very, very human terms, right? I did not even define what it means to go through a bridge and all that, right? You just know what I mean. What I'm looking for is simply a translation to this model. In this model, where I'm using the words points and lines, what does it mean? What does it mean? If the answer to this is yes, when would the answer to a question here be yes? Right? That's all I'm looking for, just a translation, nothing more than that. Yeah. Yes. Okay.
Trace the graph, we have to trace every edge without lifting the pen.
Okay, so some of you have, now you're getting the hang of what I'm asking. So apologies if I did not phrase my question properly in the beginning. Now that you're getting the hang of it, try to also think, how would you explain the same thing to a 5-year-old without explaining anything, right? So I'm sure some of you have nephews and nieces, right? So if you have to explain to one of them, or just siblings, I guess I'm too old, so I'm thinking of nephews and nieces, but yeah, maybe you just have siblings who are much younger, like 5 years old or something. How would you explain to that person what they need to do in this graph, right? Of course, you don't want to tell them about Koinsberg bridges and all that. They don't have patience for that stuff, right? You have to do something more basic, right? Yeah.
And then we do that through a line. If we use that line to travel from one point to another, we can delete that. And then if we successfully deleted every single line, then that means that we have traveled through every single bridge at least once.
Sure, that's one way of looking at it. Yeah. Yeah, exactly.
Now you need to explain this 5 year.
Yeah, yeah, go ahead.
You take a different colored pen and you have to draw on top of all those lines and cover every line without lifting the pen.
Yeah, exactly. There's one here, one here. Sort of, yeah, but I did not use the word path. I use the word. In the graph, I use the word. Yeah, line.
Wait, so if I had to explain this to a 5-year-old, like
Yes.
person,
Yeah.
you have this over here. Now take a red marker.
Yeah.
Now you have to color this in such a way that all of it gets included and you shouldn't lift your hand, but nothing is left over.
Yes, exactly. Thank you. All right. Anybody else? Right. So most of you, or good number of you, have an idea, and I guess I've just not talked to the others because there's a lot of you. Right. So let's talk about the 5-year-old version actually, which is something that almost all of you would have encountered when you were yourself that age. Right. So this is a standard question. How do you draw this figure without lifting the pen and without ever retracing over the same place, right? Of course, there is one small issue. When I reach a point, I am allowed to make that point. So I have a marker and I have a sort of like a gun that just creates a point over there, right? So think of that. I have this fancy marker and I can press one button, it will create a point, which, right? And now that's what it is. Can you draw this graph without lifting the chalk? That's basically the question, right? So same question. Rephrased. Is it possible to draw this graph without lifting the chalk? That's what it is. You all agree? Right, so I could, let's draw some graphs. Right, so this is one graph. Let's call this the Koinsberg graph. This is the Koinsberg graph. But I can ask this question for any graph. For example, let's make some drawings. Here are some graphs, right? Each of these is a different graph. This is graph G1, this is graph G2, and this is graph G3. Can you all think about it? Again, don't shout out the answer. Not interested in competitions, right? Just think and see if you can figure it out. If you figure it out, just raise your hand and I'll come and talk to you, right? And you can discuss with your neighbors. Which of these graphs can you draw? Amongst these graphs, which ones can you draw without lifting the chalk, right? And you have this nice feature, you can shoot and create a point. Maybe I'll do one more. And in the meantime, you can also think about the following question. Here's a philosophical question. If you have a graph, let's say on 10 points or something, right? You want to convince your friend that it is actually possible. What will you show to them? And if you want to convince them that it is not possible, then what will you show to them? Which one is harder? Is it easy to convince someone that this is possible? Or is it easy to convince someone that this is not possible, right? Yeah, so anyways, just philosophical question, think about. And all four are possible. And you can also think about the Koinsberg graph, right? So Koinsberg graph is our G0. Yeah, so you have 5 graphs: G0, G1, G2, G3, G4. So I'll tell you a fun story. My nephew was actually here last year. My nephew is 8 years old. He was visiting from the US and he was very excited. He wanted to tell me all these, so he had these kinds of puzzles. Can you draw this without lifting your pen and stuff like that? And I don't interact with 8-year-olds very frequently. So I did not know how to interact. The problem is I'm a graph theorist. So I could easily just look at it and I'm like, yeah, yes, no, yes, no. And he was so disappointed. He was like, I thought I was throwing a challenge at you. And then later my partner told me, maybe with a 5-year-old you should control yourself. So yeah, I kind of killed it. Anyways, hopefully I'll do better next time. Okay, anybody else wants to talk about anything? Yeah, yeah, all? Yeah, okay. What about G0? Okay.
What is G0?
All are possible. What about G0?
Which one is
G0 is the Koinsberg graph.
All
Okay.
are possible except G0.
Okay. 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 All possible. What about G0? Yeah. Okay. G0. Okay. Okay. G0 is not possible. What about the others?
So G1 is possible.
Hmm.
G2 is possible. G3 is not possible. G4 is
Well, I drew the graphs without thinking, right? I just drew them. Turns out all the graphs I drew, for all of them it's possible. So the answer for all of these is actually possible. Give it a try. This one is actually not possible. Yeah? Okay. So let me add one more line to the G2. I'm going to add one more line. This is G, I don't know, 5. I just took G2, I added one more line to it. Okay, make it possible. Yeah, make a drawing and check it's possible or not. Sorry. Okay. 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 Convince your neighbor. Convince your neighbor. Which one? Okay, convince your neighbor. Not possible. Convince your neighbor. You're both convinced? That's good. Now convince a third person. If you have convinced your neighbor, convince a third person. Okay. Alright, so does everybody see what's going on? Do you get the gist of the questions we are asking? Yeah? Okay. So what I want to do next is, we have phrased this question in two different ways. This is the original phrasing, and this is the what we call the 5-year-old phrasing, right? You can all explain this to a 5-year-old, right? What I'm going to do now is I'm going to talk a little bit about graphs, right? So for example, I use the word point and line. Does anybody see a problem with these words? Right? So a lot of times in life, we have to choose a word for something. Do you see a problem with the words point and line? Why do you think I put them in double quotes?
Line is something that extends.
Okay. Some of those lines are not straight. Okay. Line is something that extends indefinitely. I could have used line segment. Would that be good? Instead of line, I use line segment. Sorry? Line is made up of points. That's okay. That's one word. Sorry? Line segment is a long word. That's a good point. I don't like long words. Right? So one of you mentioned that it may not be straight or something. What was that? A line may not be straight, right? Line, generally when we say line, we mean straight line, right? At least many times formally speaking, when we say a line, we actually mean a straight line that extends in both directions infinitely, right? In this case, does it matter whether I draw the line between 2 points like this, like this, do all of these matter? They don't matter. Do you all agree? It doesn't matter whether I draw my lines like this, or in any complicated fashion. Do you all agree? Line and point, these words give the impression that we are studying geometry. Right? And in geometry, the actual way you draw things matters. In graph theory, it doesn't matter. What matters is either there is a line or there is no line. That's the only thing that matters. Right? So it is for this reason that we don't use the word points and lines. The standard words we use are vertex. Some people also use node. I prefer vertex. And instead of lines, we use edges. Okay? So the reason for this choice of words is simply to convey the point that this is not geometry. The way you draw actually doesn't matter. The only thing that matters is there is a line or there isn't a line. Let's do one more example. Right? So, how many of you are on some social media? Yeah? Everybody's on some social media. Whether your parents like it or not is a different matter. Right? But you are. Right? So, social media, you can think of it as a graph. Right? How many of you are on Instagram? Yeah, okay. So some of you are on Instagram. Let's say we take all the people who are on Instagram, assuming there are no bots and all. Anyways, right. So now all these people, you can think of them as your vertices. The plural of vertex is vertices, and you put an edge between two if they follow each other. Of course, I guess in Instagram, I can follow you, but you may not follow me. That is possible. Let's suppose that's not possible. Let's go to Facebook. Facebook, either we are friends or we are not friends. Of course, you all may not even have heard of Facebook, but I come from that generation where people use Facebook, right? So either you are friends or you are not friends. What is this? This is a graph. Everybody is a vertex. You can represent every person as a vertex, and you put an edge between them if they are friends on Facebook, otherwise you don't put an edge, right? So any social media network can be thought of as a graph, yeah?
But in that case, wouldn't the edges be directional as well?
In the case of Instagram. In the case of Instagram, we will put directions on the edges. I am following you, but you are not following me. Something like that, right? But that's why I went to Facebook, because here there are no directions. So in fact, in graphs, there is directed graphs and there is undirected graphs. I will only talk about undirected graphs. Yeah, thank you. Okay. So what we have here is generally called an undirected graph. So what is an undirected graph? It has an undirected graph G. It has two things. It has a set of vertices and a set of edges. Right? This is the set of vertices. And this is the set of edges. Right? Each edge is nothing but two vertices. Basically, this edge here, B1, you can simply think of it as B1 is nothing but L1, L2. This is basically telling you which two vertices it joins. Okay? Of course, I don't like this notation. I just like to draw a graph. A drawing is much more appealing to me rather than this notational nonsense. Right? So that's what I prefer. But of course, the formal definition, I don't need a drawing. I can just tell you, here is a graph. Right? Whether you draw it or not is a different matter. Okay. So now let's try to phrase this question in the language of graph theory, because that is the language that is easiest for me to explain. Right? So how much time do we have? Another 10 minutes for this session? Yeah? Okay. So in the next 10 minutes, let's just try to rephrase this question in the language of graphs. Right? Okay. So in the language of graphs, what is it that we want to do? Let's just make a drawing. So you all said that for all these graphs, the answer is yes, you can do it, right? So let's do for one of them. For example, let's do it for this fellow, G4, right? Let me also label the vertices. So now that we are using vertices and edges, let me do it for this one. This is nice. V0, V1, V2, V3, V4. Yeah, and my edges are E0, E1, E2, E0, E1, E2, and E3, E4, E5. E3, E4, E5. Yeah, and let's draw this graph without lifting the chalk. Is that okay? So I'm sure you all know how to do it. You've already done it. So here is one way to do it. I came back to the same point, but that is not a problem. Nobody said you can't come back to the same point. You simply cannot repeat the edges. You cannot repeat the edges. It's okay to come back to the same vertex. Right? So we started here. This was our starting point. And we ended here. Right? Nobody said you have to start and end at the same point. Right? Of course, that could be an additional condition. Maybe you want as a tourist to start at the airport and come back to the airport. Well, not in 1736, but today at least. Right? Airports. So, yeah. Anyways, so do you all agree? What we have here is a drawing without lifting the chalk. Yeah? Okay. So what exactly is this? We are starting at some vertex, right? I never said that in the beginning, by the way. I never told you that you should start at a vertex, right? But right, you could start, why not start here? Turns out, if you go back to the 5-year-old question, you can just put a vertex here and the answer will not change. So, yeah, go ahead. Good point. So, we never really specified. That's the problem with, yeah, so that's the problem with the real world problems, that there is a lot of unspecified stuff. Whereas in math, it is the opposite. In math, you specify exactly what you want. And there is almost no room for ambiguity, right? So yeah, I never really said that you have to start on a landmass. We just assumed that of course a tourist will be on some landmass, But why could they not be in the middle of a bridge and then start from there? Yeah. Good point. I don't know. Yeah, so we never specified. So now I'm going to specify. Now that you're asking this, right, this is exactly the kind of thing I want. Right, so now we are going to specify that the tourist actually starts on a landmass. Right? Yes, so I'm just trying to avoid the question rather than addressing the question. I'm saying let's just go back to 1736 and actually what probably was assumed by Euler and everybody is that the tourist is on a landmass, right? Yeah, but you can think about this offline. What happens if you start in the middle of a bridge? Does it change anything, right? So these are good questions to think about offline. Yeah, good. But yeah, so coming back to the question we are starting at a vertex. Remember the vertices were the land masses. We are starting at some vertex. Then we are making sure that we go from this vertex to another vertex using an edge joining the two vertices, right? I cannot use this edge and go here. If I use this edge, I end up here. Then I am going to take some other edge. I want to basically start at some vertex, cover all the edges without ever repeating an edge. But the rule is, I can only, in my sequence, if an edge is there, it has to be preceded by one of the two ends of that edge, and it has to be succeeded by one of the two ends of that edge, right? For example, supposing my edge is E0. On the two sides of E0, it should be V0 and V2. I can't have E0 and before E0 I put V3. That's not possible. V3 is not an end of E0. Right? So what I'm trying to do is, I'm trying to translate this into the language of graph theory. So I want to write down a sequence of vertices and edges with some properties. Right? And the answer to this question is yes, only if the graph has a certain sequence of vertices and edges. Right? And we need to just write down what are the properties of this sequence. Right? Okay? So the question I want to write is, so here is the same question. Same question in graph theory language. So the question was, is it possible to draw this graph without lifting the chalk? Right? So the question I want to write down as follows. Is there a sequence of vertices and edges, and this has to be alternating. After a vertex, it has to be an edge. After an edge, it has to be a vertex again. Is there a sequence of vertices and edges? And instead of writing so many words, I will just write down notation. V0, V is always for vertex, E is always for edge. E0, V1, E1, V2, E2. And there is a point I want to make here. In this sequence, I'm allowed to repeat a vertex. So a certain vertex Vi could be the same as Vj. This sequence I'm writing is more abstract, right? So these are just these are just basically like your variables x and y that you use in algebra, right? So is there a sequence of vertices and edges? Let's see, I'm putting Vk, then I'm putting the same, and I'm putting ending with Vk. And I want this sequence to have some properties, right? So what are the properties? Every edge, the two vertices that appear before and after, they have to be the ends of that edge, right? Let's write down the sequence here. In this example, I want to write down the sequence. I'm starting at V0. Then I remember how we traced the path, right? How we traced the graph. We drew this edge, E0. Then we drew, when we reach V2. Now we drew this edge, E3. Do you agree? This is E3. Yeah. Then we reach the vertex V1. Then we drew this edge E4. Then we reached the vertex V3. Then we drew the edge E1. And we reach V0 again. Observe that this V0 is equal to this V0. Right? I am allowed to repeat. And now I am at V0. What did I do? I drew this part, I drew this part, I drew this part, I drew this part. Now I am going to draw the edge E2. Now I reach the vertex V4. Now I draw the edge E5. And I reach the vertex V1. This is how we drew. Do you all agree? We started at V0. We drew the edge E0. We reached the bottom vertex, left bottom V2. Then we took the edge E3. We reached the top right vertex V1. Then we did the same thing with the other parts. We did this part. Then we did E4. We went back to, sorry, did I make a mistake here? We were at V1. Then we took E4. We went to V3. Then we took E1. Then we went to V0. Then we took E2. We went to V4. We took E5. We went to V1. This is correct. This is a sequence. What are the properties of the sequence? Before we go here, can we just look at the properties of this sequence? What is not repeated? No edge is repeated. But does every edge appear at least once? Therefore, it appears exactly once. In this sequence, every edge of the graph appears exactly once. And if you look at any edge, the two vertices before and after are nothing but the ends of that edge. You all agree? Yeah? So this is the property we want. We want, is there a sequence of vertices and edges such that each edge of the graph G appears exactly once. Yeah? And for each edge, for each EI, the vertex before it, Vi minus 1, and the vertex after it, the vertex before it is Vi. The vertex Vi before it and the vertex Vi plus 1 after it, these are nothing but the two ends of the edge. I never told you what the ends of an edge are, but you know what I mean, right? The ends of this edge are simply the ends of this bridge, L1 and L2 for B1, right? These two are the ends of some people use the word endpoints. I prefer shorter word. They are the ends of EI. This is it. This is the graph theory question. Is there, yeah, go ahead. This is just mathematical notation. So I'm just writing the elements of the sequence. I'm just using I and I plus 1 as placeholders. Right? So this is just so that when I phrase the question, I can just say for each EI, the vertex before it and the vertex after it. But yeah, in reality, for a specific edge, you can see here, E3, before E3 it is before E1 it is V3 and V0 afterwards, right? So that is just mathematical notation. These are concrete examples, right? So yeah, the one most unfortunate thing about mathematics is the amount of notation we use. It is ridiculous, right? It is what turns off most people away from mathematics. So that is something I want to really talk about, because a lot of people, including myself, today I am a mathematician. Trust me, from the age of 17 to 20, I used to fear and hate mathematics. That's what the excess use of notation had done to me. Like, I literally used to fear mathematics, right? But yeah, anyway, so this is just notation, and try not to get lost in the notation. Try to understand the meaning behind the notation, right? Yeah. Good. Any other questions, concerns? Is the general point clear here? So there is a second part after this, is it? So what we'll do in the second part is we will actually go deeper into this and we'll try to answer this question. Similar to how people did in history, right? So we'll try to get an answer. But of course, we have the advantage that we already have the graph theory terminology that is required to discuss all these things. But back in 1700s, the terminology was not even there. The concepts were not there. Euler had to invent the concepts, right? So we have that huge advantage over Euler, right? We already have the concepts. We just need to understand how to answer this question. Yeah. So we'll end here and we'll resume after the break.